lecture 3 of linear algebra. In the previous lecture, we were discussing about homogeneous versus non-homogeneous equations. This lecture covers the definition of elementary row operations, row echelon form or reduced row echelon form, etc. And the next step is to convert the linear system into matrices. Then we will study how to solve the equations using Gaussian elimination method. Whether or not a solution of linear system exists or does not exist. Consider a system of linear equations. Ax plus by equal to p, cx plus dy equal to q. Augmented matrices for a system of equations is a matrix in which each row represents the constants from one equation. That is both the coefficient and the constants on the other side of the equal sign. These are the constants p and q. And each column represents all the coefficient for a single variable. So this equation can be represented as a matrix like this. Each column represents the coefficient of the variable. So first column represents the coefficient of x, a and c. Second column represents the coefficient of y. And on the other side, we will write the constants. Use elementary row operations to convert the augmented matrix into this form. So the solution to this is 1 represent the x variable. So x equal to h and y equal to k. This method is called Gaussian elimination.
A non-zero row of A is a row with at least one non-zero entry. So this is one example. A equal to 6021, 0210, 0000, 0080. Here, all the rows are non-zero rows. In each and every row, we are having non-zero element except the third row.
Row contain only zeros. Next definition. A leading entries of a row of A is the first entry in a row with a non-zero value. So consider this example. We need to find the leading entry. So first row, first non-zero term is 6. Then we are having this 2. Then here we don't have any leading entries. So here we are having 8. No leading entry in row of all zeros. Here we don't have any leading. A square matrix is non-singular if it is a matrix of coefficient of homogeneous equation with a unique solution. Another definition, elementary row operations. So interchange two rows, it is the first operation. Second, multiply one row by a non-zero number. That means multiply all the entries in the row by a non-zero constant. Then add a multiple to one row to a different row. That means add to one row a multiple of another row. So we are having 3 operations. Interchange operation, multiplication or scaling. Second operation is multiplication or scaling. And third operation is replacement. So two systems are said to be equivalent if they have the same set of solutions. If the augmented matrices of two linear systems are row equivalent, then the two systems have the same solution. Then the definition of row echelon form. An augmented matrix is in row echelon form if all non-zero rows are above any rows of zeros. Second, each leading entry of a zero is in a column to the right of leading entries of any row above it. And then the fourth point, all entries in a column below a leading entry are zeros. So if a matrix in echelon form satisfies the following additional condition, then it is in row reduced echelon form. The leading entry in each non-zero row is 1. Each leading one is the only non-zero entry in its column. An augmented matrix is in row echelon form if all non-zero rows are above any rows of zeros. Each leading entry of a row is in a column to the right of the leading entries of any rows above it. All entries in a column above or below a leading entry are 0. The leading entry in each row is 1. Each leading one is only non-zero entry in its column. So some examples for this row echelon form. So here we can see that this row echelon matrices have a staircase effect. The leading ones proceed down. Look at this example. The leading one proceed down. So these circled stars can be 1. So the leading ones, so these circled stars are the leading ones. So these leading ones proceed down to the right through the matrices. So these are the leading values. Entries above to the right, above, entries above and to the right of the leading ones are arbitrary. So these values are arbitrary. This is the leading one. These values are arbitrary. So this is leading one. These values are arbitrary. But all the entries below and to the right of them are 0. All the entries below and to the left of them are 0. So all the entries below are 0 and all the entries to the left are also 0. All the entries to the left are also 0. Hence, a matrix in row echelon form is reduced form if the entries directly above each leading one are all 0. Example of row echelon matrices. These are some examples. So these are the here 6, 4, 2 are the leading values. So left of these leading values are 0. Also below the values are also 0. Below 6 values are 0. Below 4 values are 0. So this is also an example for row echelon form. Here the leading values are 1 and 3. So below 1 all the values are 0. Below 3 all the values are 0. To the left of 3 all the values are 0. Here the leading values are 1, 2, 5. And note that there is a staircase effect. So below all these values we are having zeros. At the same time, to the left of these values, to the left of 5, we have zeros. The first non-zero element in each row of a matrix in row echelon form is called a pivot. So in pivot of A matrix is, these are the pivot, non-zero element in each row, 6, 4, 2. First non-zero element in B, first non-zero element is this, 1. Next non-zero. In the next row, here we don't have any pivot element. So in this case, first non-zero is 1. In the second row, we have a non-zero 2. Third row, we have 5. So pivot of matrix are 1, 2, 5. So reduced row echelon form will be of the form. Some examples for reduced row echelon form. So look at this example. These are the leading values. Leading values must be 1. That is a condition of reduced row echelon form. So previously we studied that below values are 0. Below values are also 0 here. Then the left values of leading values are also 0. Left values are 0. In addition to that, the elements above this column are also 0. So this is leading one. So the elements above this one is 0. So D and E are examples for reduced row echelon form. Then definition, rank. The number of non-zero rows in the row echelon form of a matrix A produced by elementary operation on A is called the rank of A. So we have a reduced row echelon form D and E. How will you find the rank of D and E? The number of non-zero rows. How many non-zero rows are there in D? This is non-zero. So 1, again non-zero, 2, again non-zero, 3. So rank of D is 3. What about rank of E? First non-zero, second non-zero. Here we don't have any non-zero values. So rank of E is pivot position, a position of a leading entry in an echelon form of the matrix. The next definition is a non-zero number that either is used in a pivot position to create zeros or is changed into a leading one, which in turn is used to create zeros. Pivot column, a column that contains a pivot position. Let's consider this example. That is pivot, that is a non-zero number. So in the first row, this is the first non-zero element, leading element. So this is the pivot. In the second row, this is the non-zero element. So this is first non-zero element. So this one is the pivot. In the third row, this 4 is the first non-zero element. So this one is the pivot. In the last row, there is no element, no non-zero element. So no pivot in this row. So how will you determine the pivot position? Pivot position is the position of the leading entry. So what is the position of this one? Pivot position is 1, 1. What is the pivot position of this element? That is second row, second column. Second row, second column. What is the position of this one? Third row and fourth column. So 3, 4. Then which are the pivot columns? Column that contain pivot position. So pivot are present in this column. So this is a pivot column. First column is a pivot column. Again, in second column also we have a pivot 3. So this is also a pivot column. In the third column, we don't have any pivot. So this is not a pivot column. And in the fourth column, we have a pivot 4. So this is also a pivot column. In the last column, we don't have any pivot. So that is not a pivot column. Theorem: if the augmented matrices of two linear systems are row equivalent, then the two systems have the same solution set. In other words, elementary operation do not change the solution set. Another theorem: every matrix is row equivalent to one and only one reduced row echelon matrix. In other words, every matrix has a unique reduced row echelon form. If a matrix A is row equivalent to row echelon matrix B, we say that A has the row echelon form B. If B is further reduced to reduced row echelon matrix, then we say that A has reduced row echelon form B. Row reduction algorithm. Begin with the leftmost non-zero column, which is a pivot column. The top entry is a pivot position. If the entry of the pivot position is 0, select a non-zero entry in the pivot column. Interchange the pivot row and the row containing the non-zero entry. If the pivot position is non-zero, use elementary row operations to reduce all entries below the pivot position to 0 and the pivot position to 1 and entries above the pivot position to 0 for reduced row echelon form. Cover the pivot row and the rows above it and repeat steps 1 to 3 to the remaining submatrix. Another theorem: every matrix is row equivalent to one and only one reduced row echelon form. In other words, every matrix has a unique row reduced echelon form. Procedure of writing a solution set of a consistent system. Row reduce the augmented matrix to reduced row echelon form RREF. Express each basic variable in terms of any free variables appearing in an equation. Then write a typical solution is X as a vector whose entry depend on the free variables, if any. Decompose X into a linear combination of vectors using the free variable as parameters. So what is a free variable? A variable in a consistent linear system is called free if its corresponding column in the coefficient matrix is not a pivot column. A variable is a basic variable if it corresponds to a pivot column. So consider this example. This is a reduced row echelon form. To interpret this triangular form, we can go back to the equation notation. x1 minus 2x2 minus 4x4 equal to 0. Then here this is x3 minus 2x4 equal to 3. Finally, x5 equal to 4. So which are the pivot column? Pivot elements are present in this one. First, third, and here fifth. These are the pivots. So pivot columns are 1, 3, 5. Which are the basic variable here? Basic variables are x1, x3 and x5. So x2 and x4 are the free variables. Next theorem: for any homogeneous system Ax equal to 0, number of variables equal to number of pivot position of A plus number of free variables. Next theorem: a linear system is consistent if and only if the row echelon form of its augmented matrix contain no row of the form 0, 0, 0, B where B not equal to 0. Existence and uniqueness theorem: a linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if and only if an echelon form of the augmented matrix has no row of the form 0, 0, 0, B with B not equal to 0. Second one, if the linear system is consistent, then the solution set contains either a unique solution when there are no free variables or infinitely many solution when there is at least one free variable. So this is one example. So here we have a set of equation. This is the reduced row echelon form. And go back to the equation notation, we will get like this. So from here, we know that there is no free variable. So if the system is consistent and no free variable means there will be unique solution. That is the theorem. Another set of equations. And this is the echelon form. So this one is x5 equal to 4. Actually, here no row of the form 0 equal to 1. Then we can say that the system is consistent. Which are the free variables here? x3 and x4. So consistent system with free variables means that we will get infinitely many solution. Gaussian elimination method. First of all, we have to transform the augmented matrix of the system of linear equation into row echelon form. Then back substitution to get solution. So actually this can be applied if coefficient matrix is singular matrix and rectangular matrix. Some questions. So this is a set of equation. So coefficient matrix is denoted like this. And the augmented matrix is, in addition to the coefficient matrix, we have to add the constants also. Going to apply elementary row operation. 2 times R2 minus R1 gives, this is R2. From the augmented matrix, we have to convert it into the row echelon form. So first one, we have a non-zero entry, so that's enough. No need to change the first row. So we have to change this 1 into 0. How can we change this 1 into 0? We can apply this row operation. R2 is assigned to R2 minus R1. That is 2 times R2 minus R1. So it will give 0 minus 3. So there is no change in the first row. We have changed the second row. And converting back to the equation notation, we will get 2. This represent x. And this one represent y. Equal to 3 minus 3y equal to minus 3. So what is the value of y from this? We will get y equal to 1. Substituting y equal to 1 in 2. This is our 2. So x minus y equal to 0. Value of y is 1. So x minus 1 is 0. So x equal to 1. So x equal to 1 and y equal to 1 is the solution of the set of equations.